Alright, so this is my first attempt at a video, so hopefully this works out. If all went to plan the previous week, we should have covered kind of an intro to hypothesis test with proportions. So 9.3 is going to be hypothesis test with means. So today should be Tuesday, February 7th, starting 9.3 day 1. So since this is a video, feel free to either speed up the video, slow down the video, pause the video, whatever time you need. So what do we already know about means from confidence intervals? Well, with means, we're going to be dealing with t distributions. So they follow t distributions with degrees of freedom of n-1, or sample size minus 1. Okay? Conditions for significance tests about means. Well, we've been dealing with these conditions for the entirety of Chapter 7, the entirety of Chapter 8, and no surprise, they're the exact same for Chapter 9. So first one to check, does the data come from a well-designed random sample or is it a randomized experiment? If it is a sample, we check the 10% condition. So 10 times the sample size being less than or equal to the population, and then kind of the 3-tiered system for means. So first thing to check, is the population normal? If we don't know anything about the population, we move on to sample size. So is the sample size sufficiently large? So is n greater than or equal to 30? If the sample size is too small, so it's less than 30, we would then have to check a graph. So if these two aren't met, we use a graph of the sample data to assess the normality of the population. Do not use t procedures if the graph shows a strong skewness or outliers. Okay, it could be slightly skewed, and then it's still okay to proceed. But if there are any outliers, we can't do any t distributions. If you have to check a graph, make sure you always sketch a graph if you're using that method. Okay? So in these bottom questions, we're kind of just going to take what's given and decide, is it okay to use t procedures? So to estimate the average GPA of students at your school, you randomly select 50 students. So there's a histogram of the GPAs. So is it okay to proceed with t procedures? Well, once we know it's a random sample of 50 students, we don't even really care about the graph. So yes, we could proceed because the sample size is large, n equals 50, which is greater than or equal to 30. So we're good. Okay, second one, how much force does it take to pull wood apart? Stem plot shows the force in pounds required to pull a piece of Douglas fir apart for each of 20 randomly selected pines. Okay, well, we don't know population's normal. Say we take a look at the sample size, 20, that's not greater than or equal to 30, so we got to move on then to checking the graph. So since this graph shows pretty strong skewness, and these down here could be outliers, since most of the data is up here, we could not proceed. So no, the stem plot is strongly skewed left with possible low outliers at maybe 230, maybe 230 and 240. Okay. All right, part C. Suppose you want to estimate the mean SAT math score at a large high school. So here's a box plot of the SAT math scores for a random sample of 20 students. Okay, again, we check the sample size, 20, not greater than or equal to 30, so we got to move on to checking the graph. So, so even though this sample size is low, the box plot doesn't show any strong skewness and there's no outliers. Outliers would have been marked on as with a dot or a star, so there's no outliers. So because because there's not strong skewness and there's no outliers, we can still proceed with T procedures. So yes, even though n equals 20, which is not greater than or equal to 30, the box plot is only moderately or slightly skewed, and there are no outliers. Okay? Ding, ding, ding. Okay, so now we're going to move on to go through a quick couple formulas. So again, kind of general formula, which we would have talked about last week, to calculate the test statistic for running the hypothesis test. So test statistic in this case would be T instead of Z, T with means, right? Z with proportions. So test statistic equals statistic, so statistic would be X bar minus the parameter, which would be mu, all over the standard error of the statistic, which would be S sub X over the square root of n. Okay? Again, the standard error of a single mean, that's on the back side of your formula sheet, which I should have showed you before I left. Okay. All right, so example, healthy streams. The level of dissolved oxygen, or DO, in a stream or river is an important indicator of the water's ability to support aquatic life. Researchers measures the DO level at 15 randomly chosen locations along the stream. So here's the results in milligrams per liter of DO level. An average dissolved oxygen level below 5 milligrams puts aquatic life at risk. Do the data provide convincing evidence at the 0.05 significance level that aquatic life in this stream is at risk? Okay. So much like with our test for proportions, we're going to start off with determining what are our HO and HA, our hypotheses, and defining the parameter. So HO would be that there is no difference. The true mean is what they say it is. So it would be that the true mean, mu, is 5. And then we're testing to see, okay, if we come back to this, we're testing to see if aquatic life in this stream are at risk. Well, they're at risk if the DO level is below 5 milligrams. So then we'd be testing to see if, in our alternative hypothesis, is if the true mean is less than 5. So we got HOHA, and we got to define the parameter. So in this case, mu would be the true mean dissolved oxygen, or DO level, in this stream. Okay? Once you define the parameter, then we got to go on and say what kind of test we're going to perform. So we will perform, we have one sample, so this would be a one sample, and since we're dealing with means, instead of a Z test, this would be a T test. So we're going to do a one sample T test for your parameter, so for mu, at the alpha equals 0.05, significance level if if conditions are met. So there's our lead-in. HOHA, define what mu is, say what test you're going to do, for what, always just for whatever your parameter is, for what at whatever level, and then you always got to say if conditions are met, which if it's a free response, the conditions are always going to be met, but we have to show that we know what they are. So conditions, first one. So you would just keep going. I'm just coming back up here just to save some space. So conditions, first one, random. Next one, 10%. Last one, normal / large counts. Okay, so it wasn't random. So if you look back up in the problem, it said 15 randomly chosen locations. Okay, so it's random. So we got 15 randomly chosen locations. 10%, so 10 times, we chose 15, 150. So we're assuming there's more than 150 locations at the river, right? Technically there'd be an infinite amount of locations, but more than 150 locations to sample from. Normal / large counts. This is the one where if they give you data, just go ahead and start cringing, because if they give you the data, it's not going to meet the initial check for having a big enough sample size. So we're going to end up having to graph this. But anyway, n equaled 15, which is not greater than or equal to 30. So we're going to have to check. We're going to have to check a graph. Okay. So we're going to have to take this data, take that set of data in the table above, and when, ignore that TCDF for now. So in your calculators, so by now we put hundreds of sets of data in. So we're going to go to stat edit. You're going to go to stat edit. You're going to put your data into a list. Okay? Then second y equals to open up a stat plot. So make sure your stat plot is on. Now for this one, we either want to do a histogram, we want to do a box plot with the one that checks for outliers, or we want to do the normal probability plot. Okay, all my answer keys are going to have normal probability plot just because I think it's the easiest one to sketch. So we highlight the last one, make sure data list was L1, and then click the zoom button, zoom 9, which is zoom stat, and you get a nice little normal probability plot. So this is what you'd have to sketch. So the x-axis are your values, so DO levels, y-axis is z-scores. So you don't have to plot these precisely when you sketch it. You kind of just have to put the dots there so that it kind of resembles what this looks like. You don't have to be precise. Okay, so for my sketch, so this would be after the normal check, we'd have a sketch for a normal probability plot. So that went from 1 to 2, went from -1 to -2. We had DO levels. Up the y-axis was z-scores, and I think they were kind of just like that. So remember, what we're looking for in a normal probability plot is is the distribution of z-scores approximately linear? So all we have to say is, because the normal probability plot is approximately normal, approximately linear, sorry, is approximately linear, the sampling distribution of x bar should be approximately normal. Okay? So that would be our full check of conditions. Okay, the normality one is a little longer because we had to make a graph. And then we got to say, because this graph, this normal probability plot is approximately linear, the sampling distribution, so our sample data, should be approximately normal. That means we can then proceed with using t procedures. Basically find t-squared. Okay? So after conditions, now we're going to move on to the actual calculation. So from your formulas formulas above, it says test statistic, so in this case t, because we're dealing with means, equals statistic minus parameter. So x bar minus mu over the standard error of the statistic. So standard error is the standard deviation divided by the square root of n. Okay? Well, this problem did not give us the sample mean and the sample standard deviation, right? It gave us all the data points. So we have to get those. So you already had to put the data into your calculator to make the graph. So now we need to just take this data set we have in here and get the sample mean and the sample standard deviation. Okay? So from your home screen, stat over to calc, 1var stats. We've done this maybe 1,000 times. So all the data is in list 1. We didn't put anything in list 2, so we don't want a frequency list. So just 1var stats of list 1. Okay, and we get an x bar, a sample mean of 4.771. And we get a sample standard deviation, not sigma. We want the sample standard deviation of maybe about 0.94. Okay. After this. So statistic, sample mean, minus the population mean. Mu up above was 5, so we're putting 5 in there. Sample standard deviation, got that from 1var stats, over square root of n, square root of the sample size. Okay, now there's a couple different ways to proceed from here. First thing I'm going to do is show you the easiest way. So eventually from this, we need what t is going to equal, and then we're going to use t to get a p-value, so we can then get our conclusion. Okay, so the easiest way to do it, I think, is, and we should be somewhat familiar with this route already, is stat over to test. So this is where we would have been last week with the one proportion t-test. So this time though, we're running a t-test. Okay, so it's the second one down, t-test. So two different ways you can do it. You can either do it with data, so this is just going to pull everything from your list. So if we do it this way, we would put our mu in as 5, list 1, okay, and then for this, not equal to, less than, greater than, come back to what the alternative was. So alternative was that mu was less than 5, so we want to have the less than 1 highlighted, and then calculate. Okay, if you ever have to do the stats one, the stats one already just pulls in the sample mean and standard deviation from your data. So both routes are the same. They're going to get you the same answer. So come down to calculate. So then when it runs the t-test, the two things we really care about here are t and p. So the t is what all of this is going to equal, negative 0.943. Now, we still need a probability statement. So since this is negative, we're going to find probability less than that. Okay, and whatever you're writing for your probability statement, this less than should also match the alternative, which was less than. So we're finding the probability that t is less than whatever we got for a t here, so negative 0.43. And that probability equals the p-value. So that's going to equal about 0.18. Okay? Another way, so that's all you would need for that. Then you could use that p-value to write your conclusion. Okay, something you're going to have to do, not for this question, but eventually for a multiple choice question, is just given what t is. What was that? 943. Okay, eventually, just given a sample size and a t-score, you're going to have to find probability. okay? And that's not enough information to run a full t-test on. So if you have to find probability from a t-distribution, since it's not z, we're not going to use a normal distribution, we could use a t-distribution. So if I had to find this, probability that t was less than negative 0.943, another way I could do that is go into the distribution menu, so second vars, where we've been a lot, and instead of normal CDF, the second one down, we would use TCDF, the sixth one down. So TCDF asks you for three things: lower, upper, and degrees of freedom. Well, if we're finding less than negative 0.943, lower, negative infinity, up to the value, and then degrees of freedom is sample size minus 1, so 15 minus 1, so degrees of freedom 14. So that, if we did everything right, should give you the same p-value as we got with the t-test. About 0.18, 0.181. Okay? Again, you wouldn't have to do this for that test. I'm just showing you that because you're going to have to do that on a multiple choice question later on. So coming back to our question. So after we ran the t-test, we got a p-value of 0.18. So what are we going to do? Well, that's higher than our significance level. So because our p-value is high, 0.18 was greater than 0.05, what are we going to do? If the p is high, we fail to reject HO. If the p is low, reject HO. So because our p-value is high, we fail to reject HO. If we fail to reject HO, we're not rejecting HO, which means there is not convincing evidence for the alternative. So there is not convincing evidence that the true mean DO level in the stream is less than 5, I think that's right, 5 milligrams per liter, okay? So if we fail to reject HO, there's not evidence for HA. HA was that the true mean was less than 5. So if we fail to reject HO, there was not evidence for that, okay? All right, part B of that. Given your conclusion to part A, which kind of mistake, type 1 or type 2 error, could you have made? Explain what this would mean in the context. Well, if we fail to reject HO, that means it's possible that we made a type 1 error. Or type 2 error, sorry. Because we failed to reject HO, it's possible that we made a type 2 error. If we did, then the true mean DO level mu in the stream is less than 5 milligrams. 5 milligrams per liter. But we did not find convincing evidence with our significance test. Okay, that would imply That would imply that aquatic life in the stream is at risk, but we did not detect it. Aquatic life in this stream is at risk, but we did not detect it. Okay? All right. Let's go one more. All right. Tire manufacturer claims that its tires last 35,000 miles on average. Consumer group wishes to test this, believing it's actually less. The group used an SRS of 35 cars and calculated a sample mean of 33,200 miles. Standard deviation, sigma, that's going to be key here, sigma of the tire life is 4,000 miles. Carry out an appropriate significance test at the 5% level. Okay? Well, HO, again, statement of no difference, that the true mean is what they say it is. So that the true mean is 35,000. Okay, this consumer group wishes to test, believing that it is actually less. Well, the true mean is less than 35,000. Okay, where mu equals what? What are we talking about? So we're talking about the true mean miles the tire will last. Okay, so HOHA, talking about mean, so we're using mu, define mu, move on, say what kind of test we're going to do. Okay, this is where this one gets a little bit tricky. So we are given a population true mean to start with. We are given a sample size, so there's mu, we're given a sample size, there's n, we got a sample mean x bar, okay, and we're given sigma. Okay, a sigma of 4,000. So since we are given the population standard deviation, that means we are going to do a z-test instead of a t-test. Okay, if you remember a while ago, I probably brought this up. Okay, z with proportions, t with means, except z when you know sigma. So we will perform a one sample z-test for mu at the alpha equals 0.05 significance level if conditions are met. Okay. So first condition. Conditions. Random. 10%. Normal large counts. So random. Was it random? Yep. SRS of 35 cars. Okay. 10%. 10 times 35. Okay. Now, we're not really told what the population is. So we're just going to say, we're going to assume more than 350 cars in the population. Okay? Normal large counts. We're not told this is normal. So go to sample size. Sample size is 35. So n equals 35, which is greater than or equal to 30. Okay, so we're good, right? So the sampling distribution of x bar should be approximately normal. Okay? All right, so now we're going to move on to the calculation. Okay? So, we're using Z, right? Since we knew sigma, we're doing a one sample Z test. So Z equals statistic minus parameter. Now on the bottom here, normally it would be S sub x over the square root of n, but since we know sigma, it's going to be sigma over the square root of n. So x bar, we're told 33,200 minus the mu, 35,000, all over sigma over the square root of n, so square root of 35. Okay? So, in your calculator then, so under the tests, so typically with Z, we were using a one proportion Z test. If this is a one sample Z test with means, but we're using Z, we would use Z test, just the top one, Z test. So, probably go to stats since we didn't have to put any data in. So, we're saying the true mean is 35,000. Okay, we know sigma, 4,000. We know x bar, 33,200. Sample size was 35. HA was that mu was less than, so we're going to leave that on less than, and then we're going to calculate. So we get that Z equals negative 2.662. Okay, since it's negative, get our p-value here. So there's our p-value, 0.0039. So Z was negative 2.662, so we find the probability that Z is less than negative 2.662, and that would equal our p-value, 0.0039, I believe. Yep. So, conclusion, comparing this to the significance level. Because our p-value is low, right? 0.0039 is less than 0.05. When the p is low, reject HO. So we reject HO. If we reject HO, there's convincing evidence for HA. So there is convincing evidence that the true mean miles a tire will last is less than 35,000 miles. Okay? All right, so that is the end of day one. Hopefully that wasn't terrible. I know it probably sucks watching videos. Tomorrow will be another video, as well as tomorrow night I'm planning on having a Teams meeting. Hopefully we know a time by now. Again, I'm making this in December. An optional Teams meeting where I'll just be on Teams. You'll have an invite link. And if you have questions over any of this content, you can pop on, ask those questions, stay for the whole time, stay for a little bit, or just jump on and chat if you want to chat. Okay? Have a good rest of your day.